Alors, cette fois-ci, c'est vraiment Herman Pontzer, qui vient donc de Duke University et avec qui nous allons aborder un sujet qui a été évoqué déjà dans mon introduction ce matin et qui a été abordé par certains des intervenants, qui est la question de l'énergie. Hein. Dans tout ça, il y a un sérieux problème d'énergie et c'est un sujet central dans les questions évolutionnaires chez les hominines. Et Herman a beaucoup travaillé là-dessus.
Merci beaucoup. I'm going to speak in English. I'm sorry for that, but I promise that my French is worse than your English, so we're doing everybody a favor here. All the slides should be translated into French. Dan Lieberman kindly agreed to do all the translations, so if they're wrong, you can talk to Dan afterwards. As Jean-Jacques nicely introduced me, I believe he said that I like to work on energetics in humans and other apes, how we spend energy and take it in and spend it on different tasks. And I'm going to be speaking about one aspect of that today, which is this question of endurance and what are the limits of energy expenditure. I heard some of this in the last talk, which was fantastic. Often, when we think about endurance, we're thinking about it in this kind of context here. This is very similar to what we saw in the last slide, last talk, which is we think about how fast can I run or how long can I run for. And so if I ask you, how long can you do something? If endurance is how long can I maintain a certain effort, I can ask, how long can you run? We understand intuitively, we all know, that how long I can run, how many minutes I can stand it, will be determined by how fast I go. And so if I run slowly, I can run for longer. If I run fast, I can only run for a short time. We know this. This is intuitive stuff. And so if we put the world records for various length races here, it looks something like this. This is human world records. This is a marathon is about there. This is everything shorter than a marathon. This is a 200 meter. This is everything ultra marathons up here. And so just like we would expect, the faster I go, the shorter the amount of time I can do it for. So we can think of endurance as having kind of a time element to it and having this sort of sloping ceiling. And so this is true if we look at the Olympics as well. So when we watch the Olympics in a couple of weeks, we'll see 50 km race walkers and our marathoners and our 400 meter runners. They're all going to be playing along, they'll be behaving themselves, playing by the rules of what human endurance looks like. And we heard a lot of fantastic talks this morning thinking about how humans, this is the human ability curve here, how humans differ from other apes. And as Dan said this morning, other people have mentioned it too, humans are incredibly endurance adapted. By the way, this interesting step change here is around the speed at which we have to use our anaerobic metabolism. And so up until about 5 or 6 meters a second, if you're well trained, you can rely almost entirely on aerobic metabolism, just oxygen. And after that, you begin to use a little bit of anaerobic metabolism for your race, and your ability to maintain that speed drops off dramatically because it's really hard to run anaerobically. And that's why marathons are so interesting, because marathons are run right on the edge of aerobic versus anaerobic. Okay, but so humans have an amazing aerobic capacity, there's no doubt about that, and we can tell that if we compare that to the chimpanzees. It's hard to get good VO2 max data for chimpanzees, but as far as we can tell, these are the best we can do, and it's not anywhere near what humans can do. So even if we're a little bit underestimating, it's nowhere near what we can do. So if we want to think about the origins, the evolutionary origins of our endurance abilities, we can start here. Chimpanzees have low VO2 max. They have that slow twitch muscle. Their legs are under-muscled for their body size. And so they're stuck here. And over the course of our evolution, we've been able to push this envelope up further, and this is what we're able to do, and this is what our Olympic athletes are able to do. So we've heard parts of that story all morning and into the afternoon about the changes in our legs and the bone structure, the muscle structure, the mechanics that has allowed this to happen, as well as things like changes in our hearts, changes in our muscles. But all of these are one-day events. And what I want to think about today and focus on is something that we might not have focused on as much, which is how do we get there? How do you get to the Olympics? Right? You don't just show up and run a marathon. You don't just show up and jump in the pool and win a gold medal. You have to train for weeks, right? Months, years. Sometimes we have events these days, ultramarathons that might last more than one day. And so I want to think about a kind of different level of analysis, a different kind of endurance, which is what happens to our bodies, what are our limits of endurance over days, weeks, or even months. And we're going to find out that there are similarities and some differences into what we just saw with the one-day events in the last slide. Okay, so to do this, to ask what's the limit of our energy expenditure, of our endurance over this time frame, so the units we're going to use, the measurable that we're going to use is energy per day. And we're going to ask, what's the limit to energy expenditure per day? How many calories or joules? Do we prefer joules or calories in France? Calories, good, thank you. So if we prefer calories, how many calories per day can I burn? What's the limit of that? Well, if we want to ask that question, we need to be able to measure calories. And here's how we do it. So if we have our athletes, we can have them drink some water. This is a special technique that's only been available for the last couple of decades. It's called doubly labeled water. So we have some water, of course, is H2O. We have water that has a special deuterium H and a special oxygen 18O. You drink that, great. Then it goes into dilution in your water, in your body water. Over time, of course, through urine and sweat and water vapor that you breathe out, you lose both of those isotopes in the water that you lose over time. But you also, through a trick of physiology, you also lose the oxygens in the CO2 that you breathe out. And of course, you know that if I have a measure of CO2, I will also have a measure of energy, because I can't make CO2 without burning calories. I can't burn calories without making CO2. So I have a very accurate measurement of energy per day with this technique, because with a little bit of mathematics, I can subtract the rate of deuterium loss from the rate of oxygen loss, and I can get CO2, and that gives me energy per day. So this is the best way, in fact, it's the only way to really measure how many calories you burn every day in a normal daily life. Right? If you go outside of a laboratory, this is the way you need to do energy measurements over the course of days or weeks. And so all the data I'm going to show you today are from this technique, and so they're real measurements of calories per day. And we can ask then, if we measure this in as many crazy scenarios as we can, in the most extreme events, the most extreme training, whatever, what are the limits that we can find when we explore this in humans? Well, let's start here. I'll start with my first study looking at endurance limits in humans. And it was this really crazy race called the Race Across the USA, organized by that guy, I believe. It looks like Kevin Hatala, but it's not. It's Bryce Carlson. And they ran from Los Angeles to Washington, D.C. And that was 6 marathons a week for 20 weeks, 3,000 miles, or 5,000 kilometers. That's a lot of running, right? And so we measured energy expenditures along the way, so we knew how many calories they're burning for that 5-month event. And so I'm going to show you all these data like this. Here's how long the event took. So in their case, it was 120 days. And this is how many calories they burned. And I'm going to show it to you in a funny way for some of these graphs. This is as a multiple of your resting metabolic rate. Right? So if you're asleep, that's 1. If I burn twice as much energy as sleeping, that's 2. If I burn 10 times as much energy as I am sleeping, that's 10. Okay? And it's just a way of being able to compare across studies. Here's the Race Across the USA. They're about 3 for 120 days. And it turns out this has been done in other studies as well, using the same technique. So for example, the Tour de France, which is happening right now. This is the 1985 Tour de France. There, look, they were able to burn more calories, but it's a shorter event. It's only 23 days. And this is the guy who has the Appalachian Trail record. It's a 2,000-mile trail. Ironman triathlons, right? And the rest we can fill in like this. Isn't that interesting? So we have another kind of sloping relationship like we saw with one-day events, but now we're talking about over multiple days. Okay? And we can sort of fit a curve to this. And anybody care to guess what's out here? What's a really hard event that lasts about 9 months? Anybody care to guess? Boom. Yeah? So pregnancy is as difficult as an Ironman triathlon in some ways, if you want to think about it that way. It pushes the same limit. Yeah? And so, okay, so now we have a nice story. We seem to have mapped out the very limits of human endurance. And in fact, if we measure daily life in hunter-gatherers, farmers, you and me, everybody, this is 130 populations, lives underneath where this flattens out. We all live underneath this ceiling, and for a short amount of time we can go up, live up here, but for long periods of time we're stuck here. Okay. And so we suggested that this is a metabolic ceiling that you cannot live up here, not possible. Well, that's an idea, and it was based on data that we collected, but other people too, and we weren't trying to break the ceiling, we just wanted to sort of map out what was there. So now we can ask the question, if you're a scientist and you have what seems to be a nice rule, of course you want to break it. So can we break it? And so the last couple of years we've been working on 2 projects to try to break the metabolic ceiling. The first is with ultramarathon runners. This is work with Drew Best and Amanda McGrosky. This guy has all sorts of world records, it turns out, for running long distances. He's by himself a lot, apparently. It's okay. And so we can do things like measure how many calories you burn per day versus how much you run every day. And we're going to do this for a lot of different events. And so just to give you an idea, some of these people run 150 kilometers a day and burn 12,000 calories a day when they're doing it. This is a lot. You can't do a whole lot more than that. But do they break the ceiling? Okay, so we can ask the question, when they're burning this many calories a day, and we know how many days they're doing it for, we know how long the event was, do they break the ceiling? And it turns out, so far, a 250-mile race, the fastest race across Arizona, nope. Everybody's still playing by the rules. Nobody's broken through the ceiling yet. What about normal daily life? I use the word normal very carefully because I don't know that this is normal. But if you look at their normal daily life, averaged out over the course of a year, that's what they're doing. So they're hovering right at that limit that we would expect them to. So more than you and me, you and I live here, and these guys live here. But nobody is up here. Can't happen, apparently. But of course, what you would really want is ultramarathon runners that were pregnant, right? So that seems impossible, unless you can find some. And so this is a study that is being led by my graduate student, Shrishti Sadir. We call it the Marathon Mom Study. And these are women who, before the pregnancy, were running at least 32 kilometers a week. Many were running much more. Getting at least 300 minutes of exercise a week. The average American gets 10. So it's a lot. I might be off on that a little bit, but it's a lot. And then in the study, we measured energy expenditure at 15, early pregnancy, and 32 weeks, late pregnancy. We have 20 that have been done so far. All the babies are healthy, I'm happy to tell you. So no problems here. And I want to be really clear. We're not asking them to do this running. They're going to do it anyway. We're just measuring while they go. All right. To give you some numbers, so they're gaining body weight through pregnancy. And in fact, they gain about the same amount of weight as we would expect for mothers during pregnancy, even mothers who don't exercise. So there doesn't seem to be an effect on weight gain too much. They are still, at 32 weeks in the 3rd trimester, getting about 10 hours of exercise, hard exercise a week, still running. Some of them drop out completely. So this average is a little bit misleading. It's kind of bimodal. But about 25 kilometers a week of running, 3rd trimester. If you've been pregnant before, you know that this is phenomenal. So surely they must break through the metabolic ceiling, right? Because that pregnancy dot that I showed you before is just for a typical Western mom in the US or Europe or anywhere that's just living her normal daily life, probably not very active during pregnancy. Surely they'll be elevated above that. Boop. Nope. There's a fair amount of scatter, but the data are in that ballpark right there. I'm going to let Shristi present the full data set very soon, but I'll sneak peek right now that they're about right there. They're not breaking the metabolic ceiling. And so we can say that this seems to be, so far, we've tested it twice, we'll keep on testing it, but so far, this really does seem to be a metabolic ceiling. You can't live up here, not possible, and everybody, you, me, and even all the Olympians we know, are living right there. Okay, so where will the next Olympics take place? Here, underneath the metabolic ceiling. You have to. You cannot go above it. It's not possible. This is nice. We've mapped out a very hard limit on what humans can do. And so we've described it, and now we get to do some fun science and ask, why is it like that? Where is it? Why is it there? And so some questions that we are still working on, and so these aren't finished questions at all, but things that we're working on now and interested to talk with you about, is first of all, what's going on? Why is the limit here? For example, if we could imagine different physiological reasons for a sort of curvilinear shape like this, with fatigue and that kind of thing, but why does it flatten out here? What is it about this level that seems to be sustainable? Why is it that, and it turns out it's about 2.5 times your basal metabolic rate. Nobody is able to live above that for any amount of, really any amount of time. For a short time, sure, but not for long. Why? What's the limit? What's the 2.5 BMR limit? Our initial thought was that it might be your guts. That when you're burning all this energy, you need to put it back. And to put it back, you need to eat it, and then it needs to get absorbed into your body. And that requires digestion and absorption. And when we first published this idea about the metabolic ceiling, we took data from overfeeding studies, so you're locked in a room. I don't know if you're locked in a room. You're in a study, they give you too much food, way too much food, and you eat as much as you can, that's the study, and they see how much weight you can possibly gain. Or you do these endurance events, like I'm talking to you about, the Tour de France, race across the USA, or we have a measurement from pregnancy. And you can see that all of these studies, the amount of energy actually absorbed is around 2.5 times your BMR. A little bit of noise there, but it's not too bad. And this is how long the study was for, that's okay. And in fact, here's this daily energy expenditure. When you're gaining weight in these overfeeding studies, your energy expenditure is low. When you're in these endurance events, your energy expenditure is high. And you can see there's a relationship here that says if I am burning too many calories, I start losing weight, right? That's the line of being able to replace my calories. If I'm up here, I'm gaining weight from overfeeding. If I'm down here, I'm losing weight from an endurance event. Of course, pregnancy, you need to gain weight. That's a rule. And so perhaps this crossover point, which is about 2.5 BMR, is telling us something. It's telling us that's your body is built, that's what puts the ceiling where it is, because your body can't run long-term faster than you can put the energy back. It's a nice idea. But here's the problem. Those people right there. And for a while, I thought they were just cheating, which people in cycling are known to do. But the Tour de France is special, I thought, because they are able to have really high absorption. This is 1985. Back in 1985, there were a lot fewer rules about, a lot less enforcement about cheating, doping, et cetera, et cetera. And so I thought, well, maybe that's just because they're cheating. But actually, just recently, there's another study of athletes in the Giro d'Italia, done by my friend Guy Blasky, and they found, and these people are under much more strict regulation about what they can do, they're getting BMR absorptions of 4.5 BMR, so well over that 2.5 times. So it seems to be possible for humans to absorb more than 2.5 times BMR. So maybe the guts, maybe we don't have that all figured out yet, that why it's 2.5, because sometimes you're able to go to 4.5. Maybe it's the special food you can eat. Maybe it's the special powders and goos and drinks and whatever that's able, with those special processed foods, they can get over 2.5 BMR. Maybe on normal food, you can only get to 2.5 BMR. I don't know. We're still working on it. Okay. So that's one question, is why is it 2.5? I don't know. I still think it has to do with guts, but we haven't figured it all out yet. The second question is, why is it here? And I've put this line in here. This is a guess. I don't really know. To do these studies with chimpanzees or other apes would be basically impossible. But based on what we know about chimpanzee endurance and gorilla endurance, it's much lower than what humans can do. And so I suspect that their multi-day endurance is also quite a bit lower. And in fact, if you look at daily life PAL, these ratios for daily life in apes, we do have those data, and they are lower than humans. So it's makes me think that all apes are probably low, which means that there's been selection for humans to get pushed up higher. Now, what is that selection for? And that's an interesting set of questions, because remember, anything along here is being held by the same mechanisms, we think. In other words, the same physiology that's limiting pregnancy is also limiting an Ironman triathlon, is also limiting daily life. That's my hypothesis, and I might be wrong, but that's my hypothesis right now. If that's true, then that means that any of these points could be points for evolution to push on. So evolution could favor running, as we heard this morning, and it picks up this part of the curve, and everything comes along with it. And now we have bigger babies, which we do. Humans have bigger babies and spend more on gestation than other apes do. That's known. Or it could be daily life. We know that hunting and gathering is just hard work. So maybe it's running and other stuff too, or maybe some combination. So maybe this is getting pushed up, and if you push this up, you push all of it up. Or maybe evolution cares a lot about reproduction. So maybe there's been selection on reproduction and investment in babies, and that has pushed everything up. Maybe humans are amazing endurance athletes because of selection on babies. Right? We don't know. So this is an interesting set of questions to think about going forward. Anyhow, I'll leave it there. I'm interested to talk with everyone about this at the break, or take questions. But I just want to leave you with this. If we think about the endurance limits that we've evolved, we've heard all day today, and you'll hear, typically these discussions revolve around muscles and hearts and lungs, and that's all true. Those are really important for endurance. But perhaps the story is even more interesting, because perhaps it's also about guts and babies. And with that, I'll say merci and take questions. Thank you.
Very nice. Thank you.